Okay, so we're going to talk about chapters 18, 19 today. We're not going to go straight in order because there's some things in chapter 19 that should be said before we talk about 18. Right here is my table for today without the assumptions, which we're going to go through step by step. And the same T table. Now the top part of the table, which is the probabilities, are going to come into play today. And we're going to forget about the confidence interval part, and we're only going to focus on the top. So we're actually going to briefly jump to 19 to talk about a p-value first. Because at the end of the day, the p-value is the most important thing. P-value like that, capital P dash value. It is the probability that a sample from the same population of the same sample size produces the given sample statistic, assuming the null hypothesis is true. I'll read that again. It is the probability that a sample from the same population of the same sample size, depending on the context, produces the given sample statistic, assuming the null hypothesis is true. In essence, this is a conditional probability. Probability of parameter equals a number given H naught is true. If you can't read anything, let me know. So that means the first question is, what's the null hypothesis? We usually denote it H naught, H sub 0. Anytime you see a subscript 0, it's naught, N-O-U-G-H-T. This is the null hypothesis. This is our assumption of how the world works. That's a slightly informal way to say it, but it's whatever we're starting with. It's what we think is already true. So the p-value is the probability that we get whatever sample statistic we get, assuming the null hypothesis, our assumption of how the world works, is true. Because we always have to assume it's true, otherwise we don't know anything. And we're going to use hypothesis tests to prove or disprove our null hypotheses. And some of the homework examples are real life examples of how people use hypothesis tests to, examine things in mostly in science fields. I know if you guys are psych people, maybe you should take in psych stats, but p-values are used a lot there to hypothesis tests in general are used in every single field. When you want to check if there's really an association between two things, you use hypothesis tests. So this is kind of it's the culmination of everything we've done. And this is really how confidence intervals and hypothesis tests are the main way of how stats are used in the real world, which you'll see as we do more of this. So then we have H sub A, that's a capital A, is our alternative hypothesis. After, let's say, running some tests, we say, hey, maybe our mean isn't 20. And that would be our alternative hypothesis. It's what we think might actually be the truth. For whatever reason, our null hypothesis isn't working. We're going to try something else. And our hypothesis test is going to help us conclude which one of these two things is more likely to be true. Because probability is never a certain thing, you can't ever 100% say one of those is true, but it's giving us evidence to decide which one we want to follow. So those are our hypotheses. Then we'll have our assumptions and conditions, which will be different. In this chapter, it talks about both mean proportions. We'll get to that. So there's always a few steps. It's hypotheses, assumptions, your standard deviation, your z/t/chi-square score/f score. Those are all basically the same thing as a z-score. Your p-value, and then you conclude. So you set up your hypotheses, you use your assumptions to verify that whatever model you're using, you can use. You do a little bit of math, you find your score, and then you go to one of the tables and you find your p-value. And then you compare that to what's called a significance level. And then you make your decision. So, next thing we want to talk about is a significance level. We usually call it the Greek letter alpha. This is going to be a decimal. Usually we go with 0.05. The confidence level, which we've already worked with, is 1 minus alpha. So an alpha level of 0.05 or 5% corresponds to a 95% confidence interval. Significance level, alpha. Like statisticians, they choose the alpha level. No one's telling them what it is. What can you read? Okay. So yeah, at the beginning of every hypothesis test, if it's not given to you, which on a test it should be, just say alpha is 0.05. Just keep it simple. The most common ones, though, are 0.01, 1%, 0.05, 5%, and 0.1, which is 10%, corresponding to 90, 95, 99% confidence intervals. If your p-value is less than alpha, you reject the null hypothesis. And if it says interpret your hypothesis test, you just say we reject and then write out whatever the null hypothesis is, or we have evidence to reject the null hypothesis. If p is greater than alpha, you fail to reject the null hypothesis. You do not accept the null hypothesis. There's a subtle difference there. The example I use in office hours is if you go to court, at the end, the jury rules you guilty or not guilty. They don't rule you innocent, they rule you not guilty. Because, you know, no one truly knows besides whoever was at the crime. In this sense, it's because maybe it's just this one sample. Maybe this one sample gives us a really small p-value, and the next one gives us a big one. We don't know that because we only have one sample in front of us. But it gives us evidence to reject or fail to reject the null hypothesis. If you reject, then you assume the alternative hypothesis is true. If you fail to reject, you keep the null hypothesis. Does that make sense so far? So the interpretation at the end is a really simple sentence. We reject the null hypothesis that blah, 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 period. So now let's go through this for proportions. I have the table. It's on the midterm 3 things. It's this. But I'm going to rewrite it so we can go through it step by step. And I'll do both at the same time. So the first step is you need to determine which test you're using. And you do that by looking at the parameters. For proportion, you only need n and p hat. For a mean, you need n. You're always going to need a sample size. Your sample mean, your sample standard deviation. It's the same as for the confidence interval. which is important because you can make a confidence interval from a hypothesis test. Then you have your assumptions. So first is your randomization condition, which is the independence assumption. Then you have your 10% condition. Sample size is less than 10% of the population. The only way this can really be violated is if you have a really, really small population. Like if there's a really rare disease that like 2,000 people on the planet have, you have a sample size of 500, that violates the condition. But in general, like it's really hard to violate that condition. And then you have your success failure condition. It is basically the same thing as you know it, but it is slightly different. It is NP naught is greater than or equal to 10 and NQ naught greater than or equal to 10. The Q naught, the P naught and Q naught is what is your baseline value. It's the value you're assuming is true, not your sample proportion. For the mean, it's also a randomization condition. Means the same thing. You're always going to need a randomization condition / independent assumption. And you have the nearly normal condition, which just means unimodal and symmetric histogram. Sorry. So you need a random sample and a unimodal and symmetric histogram. So the left is justification for using the normal curve. On the right is a justification for using the T curve. Those are your assumptions. Once you get them out of the way, you got to do them second because the next things are going to be reliant on your distribution. So next I do. So the standard deviation of P hat is square root P naught Q naught over N. It is not your sample proportion. It is, again, P naught is the baseline value that'll be given to you in the question. For here, it's what you expect it to be. It is S over square root M. Next. Now you put it all together. Sorry, this is Z-score. Your Z-score is your sample proportion minus your baseline proportion over the standard deviation that you just calculated. The T-score is your sample mean minus your starting mean, your baseline mean, mu naught, over the standard error. From there, you go to the Z table or the T table, you find your P value. And then conclude. I mean, yeah, you can find this online. I just didn't put the conditions in the table. Any questions on the procedure? Oh, hold up. I didn't put the hypotheses. That's important. So your null hypothesis is P is equal to P naught. There is always an equal sign in the null hypothesis. Always. There's no exceptions. Something always equals something. And then it's either not equal to, greater than, or less than. Any of those three symbols. If you see a multiple choice on the next test and the null hypothesis says mu is greater than mu naught, it's automatically wrong. There always has to be an equal sign in the null hypothesis, and there can never be an equal sign in the alternative. can be any of these three symbols. Sorry about that. You assume you know what your P or mu is, and then you're trying to see if it's not that, if it's different in some way. Now, not equals to means less than or greater than. So if I have the null hypothesis is mu equals 2. So let's say 2. If the alternative mu is greater than 2, that means this, right? If I have mu is less than 2, that means this. If I have mu is not equal to 2, that means, well, that means if this is a normal curve, that mu is greater than positive 2 or less than negative 2. So we call not equals to a two-sided alternative. Less than or greater than is a one-sided alternative. And what that literally means is if it's two-sided, you just double the p-value from the one-sided case. Yeah, no? If this is a number line, like 2, greater than means this, less than means this, not equals 2 means both. Everything except that 1.2, yeah. But if we're looking at a t or normal curve, this is how you'd represent it. T is greater than positive 2 or less than negative 2. And since they're both symmetrical, this p-value over here, this area equals this area. So you can always just find, you always find the one-sided p-value, and if it's two-sided, you just multiply by 2. How does everyone feel about that? Because drawing this picture correctly, well, drawing it incorrectly means you'll probably get the wrong p-value, even if you did everything else right. Okay. So let's just go back to p-value. Here's definition. If your p-value is less than alpha, first of all, that means it's a really small probability, right? Let's say alpha is 0.05. So we have something that has a less than 5% chance of happening, assuming the null hypothesis is true. That is a rare event, right? You know, even 5% is 1 out of 20. Even obviously any number less than that is rarer. If your probability is less than your alpha value, your significance level, that means, assuming our initial conditions are true, this event is so rare that it makes us reconsider that if our initial assumptions are true. So that's like, if something only has a 1/20 chance of happening at random, and it happens in a bunch of samples, maybe it's not the samples that are wrong, it's our assumptions. And that's the point of the p-value. If it's so small that we need to take a second and be like, wow, that's like so rare, we come to the conclusion that, hey, maybe our initial condition, our null hypothesis, is wrong. And that's like the essence of p-value. That's why it's so important. Does that make sense? So a big p-value, you know, if you get a p-value of 50%, right? That's not significant at all. You know, 50% of the time is quite often. But whenever something's rare, that makes you, like, this is how p-value hypothesis tests were first made. You know, scientists thought, you know, maybe gravity was like 12 meters per second squared instead of 9.8. They did some tests they keep saying, hey, it's like around 9.8. They do a hypothesis test, the p-value is really small. They say, hey, maybe our gravity coefficient's closer to 9.8. And that's how like physics and stuff has like, or anything where you guys have found like constants and stuff, it's through repeated hypothesis tests that they keep narrowing down, hypothesis tests and confidence intervals, that they keep narrowing down the answer and finding what the true value things are. Because we think something's true, we observe it isn't, we do hypothesis tests, hey, we reject our null hypothesis. Does that make sense to everybody? Anyone have any questions about that? Because it is pretty complicated. Yeah. Yeah. No. Do want to talk about chapter 19, and then we can do an example or two. So, as I said a little while ago, just because once we get a low p-value, we reject the null hypothesis, great. It is not the end all be all though. Maybe our sample is really has like, extremists in the population, or there is errors. There are things called type 1 and type 2 errors, which are the different ways of our thing not being right. A type 1 error is the probability of rejecting given H naught is true. This probability is alpha. It is our significance level. And it's a false positive. So your null hypothesis in reality is true. You get a sample, you do a hypothesis test, you get P is less than alpha, you reject it. That's what this is. Obviously, it's an error. So you want to minimize the type 1 error by not having too big an alpha level. That's why we don't have anything bigger than like 0.1. A type 2 error is the probability of fail to reject H naught given H naught is false. This is called beta. I'll explain what that is in a second. It is a false negative. Could argue type 2 errors are worse than type 1 errors. They're both bad. In like the US court system, because statisticians do hypothesis tests for certain cases, and they usually require alpha 0.05 because that's a good trade-off of type 1, type 2 error. Yeah. False positive. And then we have a thing called power. I guess we shouldn't call it P. I don't know. It's 1 minus beta. It's the complement of beta. It is the probability of doing the right thing. It's probability of rejecting H naught given H naught is false. We will never in real life have a power of 100% because then we wouldn't need statistics. But we can try to maximize this as much as possible because power is good. So obviously beta and power have an inverse relationship. Let me try to show you. Beta is very hard to calculate. You won't have to do it for this class. Let's say our alpha level is here. Our type 1 error is this area, right? Let's say alpha is 0.05. So that area equals 0.05. Now, this is based at, let's say, P naught. It's the value we assume. We assume H naught is true in this diagram. Then underneath it, Here it is centered at the true mean P. H naught is false. You draw a dotted line down here. This just says P star. That doesn't mean P critical, it's just some number. This area is beta, our type 2 error. This is really important because it shows you the relationship between alpha and beta. If you increase alpha, you decrease beta. So if you increase alpha, you decrease beta, which increases power. If you increase the sample size, you decrease alpha and you decrease beta. So you increase the power. And that's the important relationships between these things. See that from this diagram? So, the 0.05, 0.01, whatever, are agreed upon alpha levels because they have a good trade-off between alpha and beta. Okay. Now, are there any, the P critical thing? That's just like, this one? Like this? Oh, power. Sorry, power. Yeah, it's not good to use P because probability, but yeah. P for power in this case. Maybe on your note card, write out the word power just to make it a little more clear. Okay. Got about 10 minutes left. Are there any specific homework problems you want me to go over before I collect the homework? I will go over it before I collect it. Yeah, Tito. Which chapter? Which chapter? This is a really good problem. Okay. Well, actually, well, it's not as good as I thought it was. Yeah, okay. 8B. Okay. That's fine. So that's our H naught. P greater than 0.05. Notice how this is a one-sided hypothesis test. So that's the information you are given. So what are the numbers for this question? Oh, I see what it means. Okay. So you want to find the normal curve with alpha where this area is 0.05. That's what's asking you. So you got to back solve a z-table. Now, here's a trick. Whenever you calculate a z-score, if you go to the negative number, it gives you the p-value. If you go to the positive number, it gives you 1 minus the p-value. So if you have like a z-score of 1.5, when you go to the table, go to negative 1.5. And that's your actual, because p-value should always be a small number. For example, if I go, this area means this area is 0.95, right? So the z-score corresponding to 0.95 area is Well, we know this, it's 1.645. If you go to the z-score corresponding to just 0.05, well, that's negative 1.645. You guys see what I mean? So if you go to the negative version of the z-score, you get the exact p-value. And I'm pretty sure that's what it's asking. Anyone want me to do a specific hypothesis test? You guys tell me which one. I don't know which problems you had. One. I'll give me a question from chapter 18, preferably. 46. Artist experimenting with clay to create pottery with special textures when experiencing difficulty with these special pieces. About 40% break in the kiln during firing. Hoping to solve this problem, she buys more expensive clay from another supplier. She plans to make and fire 10 pieces and will decide to use the new clay if at most one of them breaks. Okay. Well, from that question, she said, it says 40% break. So P has 0.4, and you want to use 10 pots. So we have those numbers. So let's just do this test. The null hypothesis is that our proportion is 0.4. They're assuming that 40% are going to break. Oh, I'm on the wrong chapter. Sorry, I'm on chapter 19. I'm like, wait a second. This doesn't seem like what we're telling. All right, do over. Hot dogs. Okay. They reference another question. They test 40 hot dogs, N is 40, to see if their mean sodium content was less than the upper limit of 325. The mean sodium content for the sample, X bar, is 322 with a sample standard deviation of 18 milligrams. Now, you want to say mu, population mean, equals. So in the first sentence, to see if their mean sodium content was less than the 325 milligram upper limit set by regulations. That is your mu naught, 325. And they said less than, right? So it is a one-sided test. Everyone go with that? So, randomization condition. Sure, they probably randomly chose the hot dogs. On a test, it'll be a bit more clear. These homework questions, not really. The other conditions. Nearly normal. Sure. Especially for homework problems, you can just kind of assume it. You know, it's a nutrition lab. So, you know, you can assume the lab knows how to do a hypothesis test properly. Yeah. Then we gotta do some math. Standard error is our sample standard deviation of 18 over square root of 40. Someone tell me what that is. The standard error is always going to be less than the standard deviation, which is good. 2.85. Okay. Then you want your t-score. So it is your sample mean of 322 minus your mu naught over 2.85. So this is -3 over 2.85. If it is a negative number, since it's symmetrical, you can just assume it's a positive number. What's this t-score? Someone plug that in for me. What? Okay. So on the table, we'll look for positive. And one thing I forgot to do, degrees of freedom is 39. Just n-1. Now, so we go to our table. There's no 39 degrees of freedom. We'll go to 35. So our t-score is 1.05. That is less than the first number on this list. If you go up to the top, the one tail is 0.10. We have a smaller t-value. Does that mean our p-value is greater than 0.10 or less than 0.10? Let me draw it over here. This is let me draw it right. 1.306. This area is 0.1. Now we have 1.05. Is this area greater than or less than 0.1? Or all of this area? Greater than or less than? Yeah. So what you write is just p is greater than 0.10. Usually on the test and stuff, you will have problems like this where your number, so if your number is to the left is smaller than the leftmost number, you say p is greater than 0.10. If your number is to the right, if we had like it was 3, that means it's less than 0.005. And if it's in between 2, you say it's in between the two p-values. Like if you have, let's say 1.4 right there, right? You say p is between 0.05 and 0.1, like that, if it's in between. Does that make sense?
I quickly go over what you did with you found what's related to your pod.
Yeah, so I went to the table. We have degrees of freedom, there's like 39. So you go to the 35 row. Wait, what are the numbers? I think it is. Yeah, degrees of freedom 39. You go to 35. You have 1.306, right? That's bigger than 1.05. So since it's to the left of the table, that means your number is more towards the middle, which has a higher area. You don't know exactly what. This table just only gives 5 columns. In reality, there's a lot more. So you have to say p is greater than 0.10 because it have more area than 0.1. You just don't know exactly how much. If you plug into a computer, you could find out. But with this table, you just know it's greater than 0.1. So you fail to reject the null hypothesis. If it's in between 2 rows, you say it's in between the 2 probabilities. If it is bigger than any number, you say it is less than 0.005. Because that would mean you have t values increasingly to the right. If you have the 2-tail probability, you go to the top row. But the 2-tail is just 2 times the 1-tail because it's symmetrical. Okay. Any last questions before the quiz? Anything? All right. So I'll stop there. Give you your quiz.